Previously, we took a look at how the shape of a capacitor will change its capacitance. And now I'd like to take a look at what happens if you combine capacitors in a circuit. So what I've done here is I've drawn a circuit diagram. So this symbol here, where you have two parallel lines of the same length, this is a capacitor. And you are just imagine this being like a parallel plate capacitor. Now, in reality, it could be a cylindrical geometry or something else, but the symbol just imagines a parallel plate capacitor. And similarly here, this is just another capacitor. This symbol here, where you have one long line and one short line, this is a battery. And there are more than one way to draw this, but I'm choosing this particular way of drawing it for a reason. The long line corresponds to the positive terminal of the battery and the short line to the negative. So the way I like to remember this is to think that the negative terminal looks kind of like a minus sign. So be very careful in drawing these so that your batteries don't turn into capacitors. And then the lines themselves are just wires hooking them up. Technically, it's any conductive pathway, but for now, we'll just say wires hooking them up. And since wires are conductors, when we're in equilibrium, the electric field inside will be zero. If we imagine that these are ideal wires, there will be no difference in voltage anywhere on any of these wires. And so this gives us a test for finding if capacitors are in series or parallel. The way you do this is you just pick some random colors. I'll pick, say, this one here. And you just literally just start drawing around the circuit diagram like this, never crossing over a line. So you just kind of go around like that. Never cross a line in the diagram. Come back. There. You've identified one voltage zone. Because the electric field is zero everywhere and these are conductors, the potential has to be the same everywhere. And since by convention we say the negative terminal of the battery is zero, that means that this entire zone will be at plus the battery EMF. Then you just go and pick another color. Let's say this one here. And you find another chunk of circuit. Like so. And you do the exact same sort of process. And everything here is at 0 volts by convention. And you could choose it to be something different if it suits you for the problem. But if you don't say anything, people will assume that you mean 0. So this is how you know. These two devices are in parallel because they share common color pairs. So we got blue here, we got green here, we've got blue here, we've got green here. That's how we know it's parallel. It's not good enough to just say what the voltages across them are. We could conceivably have one capacitor that's got a 0 and a plus E, and another one here that's a 0 and plus E. But somehow they're isolated on the plus E side, and the colors don't match. If the colors don't match, it's not in parallel, even if the voltages are the same. So here what we're looking for is matching pairs of colors, blue and green, blue and green. Okay, we're good. These two capacitors are in parallel. All right. So the goal is we would like to replace this parallel combination of capacitors with one equivalent capacitor that does the same job. Or we could just say, what is effectively the job of these two in parallel doing? Well, what do you mean by the same job? Well, from the perspective of the battery, what does it do? The battery just moves charge. So it's going to say, okay, I moved electrons around. until I had a charge of plus Q up here and a charge of minus Q down here. Now here we would be looking at saying, well, this is plus Q1 minus Q1 plus Q2 minus Q2, like that. But from the battery's perspective, how much charge did it move? It moved Q1 plus Q2, or Q, because the battery doesn't know how many devices it's hooked up to. So we have to demand that Q in this circuit be equal to Q1 plus Q2. Using the fact that Q equals C delta V, we can say that this is C equivalent times the voltage across this. Well, this is the same deal. This region here is at 0 volts. This region here is at the battery EMF. So the voltage across this device is the battery equal to the battery EMF. Similarly here, this will be C1 times the battery EMF, because we said the EMF minus 0, plus C2 times the battery EMF. And then we can cancel our EMFs, and we are left with that the equivalent capacitance is C1 plus C2 plus and such up to Cn. If we say have n capacitors, this relationship extends. So let's just do a quick example of that. So first off, I'll start by drawing a seemingly complicated looking arrangement of capacitors. Let's say this one is 1 microfarad. We'll say this one is 2 microfarads. We'll say this one is 3 microfarads. There. When you see a dot, that just means attach the wires together. All right, well, what's the equivalent capacitance of this? Well, we need to figure out, is this in parallel or not? It could be in series, or it could actually be neither. I haven't given the rule for things being in series yet, so I'll just do that right now. The rule for things being in series is if you pass your finger along through the devices. So here I'll just do that schematically with this gray arrow like that. If I schematically, so I'll just say this is the path of my finger. So I run my finger through the devices. If it has to not go through any junctions. Here it goes through junctions. Oops. So that means it's not series, which we'll get into in a second for how to do series. So the next question is this parallel? If it's not parallel, then we're going to have to wait a few videos until we develop Kirchhoff's laws. So let's just start mapping potential zones and see what we get. All right, so we will do this. So that's one potential zone. Everything here is at plus the battery EMF. And then let's do this and see what all falls into its potential zone. So everything here is at 0 volts. So now let's look at the capacitors. Blue, green, blue, green, blue, green. They're in parallel. So we've got three devices in parallel. We'll call this C1, C2, and C3. So the equivalent capacitance will be C1 plus C2 plus C3. So that will be 1 microfarad plus 2 microfarads plus 3 microfarads. Gives me 6 microfarads. If in some previous exposure you've already seen how resistors get combined, yes, this is the opposite of the rule for resistors. What I can do to motivate why it should add is I've been fudging here and saying, I mentioned briefly that this could be any negligible resistance connection. It didn't have to be a wire. So what if we just welded these plates together? Right? What did I do? I just made a plate that was the area of the two plates combined. So there you go. That would make a capacitor whose capacitance was the sum of the two, just because we increased the area. All right. Series is going to take us a little more effort, unfortunately, to properly understand. So, oops. So, again, same kind of idea here. Here, whoops. There's my battery. And we'll just do 2 capacitors, and I will show that now I'll just assert that it extends in general. I want to replace these 2 in series with 1 that does the same job. Okay. So what do we mean by doing the same job? Well, again, all the battery knows to do is move charge, and so it says, hey, I moved enough electrons to make the top plate plus Q, bottom plate minus Q. It doesn't actually know that there were intervening plates. So looking at this, we know that this plate has to be plus Q, and that plate has to be minus Q, like that. All right, so what about in between? Let's zoom in. So at the moment when we've charged the plates, the battery has moved the charge around for this to be plus Q and this to be minus Q, like so. So that, and at the moment, these plates are not charged. Give it a fraction of a billionth of a second, it's going to change, but we have to figure out how. So what's going to happen here is we're going to set up an electric field between these plates. So now if you're an electron sitting on this bottom plate right here, and you're free to go up the wire, like you are, let's actually put it over by the wire. So let's say you're an electron that's free to go up the wire here. You'll do that because you'll be feeling an electric force pulling you up. And so what's going to happen here is we had positive, 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 negative, negative, negative there. So now I'll just mark this off in purple here to help keep it straight. We're going to start this electric field between the outer pairs of plates here is going to migrate electrons off of this plate and onto this plate. So this plate's going to end up picking up a negative charge, and this plate's going to end up picking up a positive charge. But what's that going to do? As we're building up charge, we're going to start increasing the electric field strength here. Now, in the limit of these plates being very large and the separation being very small, this is going to amount to, this will continue until the electric field strength in purple is equal to the electric field strength in red. And then there will be no net field left in the wire, and we won't be able to move any more electrons up the wire. So in order to get these to cancel out, since these plates had the same area, it would have to be the case that this charge is minus Q and this charge is plus Q in order to get canceling electric fields. So we've worked out that both capacitors wind up holding a charge of Q. All right, so now that we know that, what remains for us is to figure out how to tie these together. And our clue here is to look at the potential zones again. So once again, let's map the potential zones. So this one here, everybody here is at plus the battery EMF. And similarly, everybody here is at 0 volts. But notice that we still got unmarked stuff. We have to pick another color and do it. So let's pick, light purple. There we go. I don't know what this voltage is. I'll call it V, and I can observe that it has to be less than the battery EMF, but greater than 0, because between the plates, I still have downward pointing electric fields. And electric field lines run from high potential to low. So this is definitely not parallel, because here we've got purple green and here we've got purple blue. We do not have matching color pairs, therefore they're not parallel. We can test for if they're series. So remember, again, here I'm just drawing this gray arrow to schematically indicate running your finger through. And here we pass through no junctions. So that means it is in series. All right. So by using Kirchhoff's loop law, we know that if I add my way up all the way around here, I have to add up to 0. So let's go ahead and invoke Kirchhoff's loop law from before. So let's just start here at this point right here, and I'm going to imagine walking around in a circle like this. So my first step is going to go from here to here. My voltage increased by the battery EMF. Now going from here to here, this was a decrease by how much? I don't know. We'll just call it delta V1. And then a decrease here of delta V2, and then get back, it's equal to 0. So I can rewrite that as the battery EMF is equal to delta V1 plus delta V2. But by Q equals C delta V is equal to Q over C. So this is going to be, looking at the equivalent circuit here, the battery EMF would be equal to Q over C equivalent. This would be Q over C1. This would be Q over C2. And since the Q's are all the same, we can go ahead and cancel them through. So we'll have a 1, and a 1. Now, a lot of books will just write it like this and say 1 over C equivalent equals 1 over C1 plus 1 over C2. I'm not a big fan of that form. I like getting it into a form where you get the final answer. So if you will write it at least as C equivalent equals 1 over C1 plus 1 over C2 plus, plus and such if there's more than 2 to our nth capacitor. So this is called adding in reciprocity. So what this means is that you would take the reciprocal of every single thing you have, add all of your reciprocals together, and then importantly, remember to take the reciprocal again at the end to get the answer. Sanity checks here are that in parallel, the equivalent capacitance should be bigger than the biggest capacitance in your circuit, and in series, the equivalent capacitance should be smaller than the smallest capacitance in your circuit. So let's just go ahead and do, to make a nice concrete example here, let's say I've got a 1 microfarad and a 2, well, let's say a 2 and a 3 microfarad capacitor in series. A lot of times we don't bother drawing in the battery. If you need to think about it, you can always imagine a battery connecting this, but you don't have to. So we run our finger through it. Yep, it passes through without any junctions, so it's in series. So we can say C equivalent here is equal to 1 over C1 plus 1 over C2. I like I like getting this into a cleaner form. So let's put this on a common denominator in the bigger denominator. So it'll be C2 plus C1 over C1 C2. And then this becomes C1 C2 over C1 plus C2. All right, now let's do it. So this is C1, this is C2. So this is 2 microfarads times 3 microfarads over 2 microfarads plus 3 microfarads. So sure enough, we're going to cancel 1 power of microfarads, and we will have 6/5 microfarads. All right. So what if you have more complicated combinations? A lot of times what you can do is you can look at your more complicated combination and you can break it down into smaller chunks. So I'm going to imagine that we've got some combination of stuff that looks like this. So what you hope you can do is you can look at this and you can immediately tell nothing's in series or parallel, that we can't make series or parallel combinations for the whole thing because you can't run your finger through everything, so it's not in series, and they're not sharing common pairs of potential zones if you map out the potential zones. But in this particular case, we can tell if we run our finger through this, there's no junction here. These two are in series. So even though we can't do the whole thing, maybe we can do that much. So let's just start by giving these numbers. All right. So if these two are in series right here, because we found that little chunk right there, we can figure out what that is. That's going to be 1 over C1 plus 1 over C2. And I just worked out that that was C1, C2 over C1 plus C2 immediately before. So applying that here, this will be 2 microfarads times 2 microfarads over 2 microfarads plus 2 microfarads. Hey, 2 times 2 is 4, 2 plus 2 is 4. It's 1 microfarad. All right. So then what we do is we just replace that with our equivalent capacitance and see if we can find anything else. So now this is a 1 microfarad capacitor. This is a 1 microfarad capacitor. 2 microfarads, 2 microfarads. So here, if I try running my finger through things, no matter what pair of capacitors I try, I have to run through junctions. So nothing here is in series. So we can look for things in parallel. In this case, just from how the drawing's done, you should probably be able to see it, but it never hurts to draw the zones. When in doubt, draw the zones. So let's draw the zones. So again here, I'm imagining that there's a battery connecting this through, but that we're just not looping all the way back to the battery. So everybody here is in that zone. And let's see here, everybody here would be attaching to the other terminal of the battery like so. And then in between, what's another color? Yeah, I guess light purple. Everybody here is on something else. And then I look at this though, and I see, hey, green, purple, that's parallel. And I found another one here. Purple, blue, here. These are parallel. So I can find the equivalent capacitances of each of these. So I will just call this, at the moment, let's just go ahead and call this C1, C2. We'll say C3 and C4 just to be not confused. So here, C equivalent would be, since they're in parallel, you add them, C1 plus C2. C equivalent here would be C3 plus C4. So this is going to be 1 microfarad plus 1 microfarad is 2 microfarads. And this is going to be 2 microfarads plus 2 microfarads is 4 microfarads. So now my circuit reduces to this. Two microfarads, 4 microfarads. Now, what you'll find is once you kind of get this rhythm going, once you find like the innermost thing is, say, if it's series, you're going to find you're alternating between series and parallel. And if the innermost thing is parallel, you'll probably be finding that you're alternating between parallel and series. So we would guess that this is probably in parallel. And sure enough, if I run my finger through it, no junctions. So it's in series. So if it's in series, the equivalent capacitance is 1 over, we'll call this C1. We'll call that one C2. 1 over C1 plus 1 over C2. I'd already worked out that that's C1, C2 over C1 plus C2. So this is 2 microfarads times 4 microfarads over 2 microfarads plus 4 microfarads. So this is 8 over 6. which reduces to 4/3 microfarads. Alrighty. In the next video, we will think about charging a capacitor and what would be the effect if we insert some insulating material, what we call dielectric, into a capacitor. See you there.